Engines are supposed to run smooth, but sometimes they don't. Instead of a clean boom, you get a violent shockwave, a mini explosion called engine knock. And the math behind it? The same math scientists use to predict earthquakes. Physics, combustion waves, and resonance. Normally, the spark plug ignites fuel, creating a smooth pressure wave that pushes the piston down. But if fuel ignites too early or unevenly, multiple pressure waves bounce around inside the cylinder. These waves interfere, creating resonance, like echoes in a concert hall. That resonance slams into the cylinder walls, and you hear it as a metallic ping. Knock. Math, explaining the wave equation. Now let's look at the math that describes knock. It's called the wave equation. Second derivative of p with respect to t squared equals c squared times. Second derivative of p with respect to x squared. Here's what each part means. The symbol p stands for pressure inside the cylinder. The term, second derivative of p with respect to t squared, is the second derivative of pressure with respect to time. In plain words, it tells us how quickly the pressure is accelerating or oscillating, basically the pressure velocity. On the other side, second derivative of p with respect to x squared is the second derivative of pressure with respect to position. That describes how pressure changes as you move through space inside the cylinder, the ripples bouncing around. The constant c squared is the speed of sound squared in the gas. This sets the pace for how fast those pressure waves travel. So the equation says, the way pressure changes over time is directly linked to the way it changes across space, scaled by how fast sound moves in the gas. In other words, pressure inside the cylinder doesn't just rise and fall. It moves like a wave, bouncing back and forth. Engineering, knock sensors. Modern cars fight knock using sensors. These sensors are basically microphones bolted to the engine block. They listen for pressure oscillations, the same ones described by the wave equation. When the sensor detects resonance frequencies, the computer instantly adjusts ignition timing or fuel injection to stop knock before it damages the engine. Twist, earthquake connection. Here's the twist. The exact same wave equation is used in seismology, the study of earthquakes. Instead of pressure waves in a cylinder, scientists model seismic waves traveling through the Earth's crust. Resonance in an engine is like resonance in the ground. Both are waves bouncing and amplifying. So the math that saves your car engine also helps predict earthquakes.